Hello, everyone, and welcome to Calculus, Extreme Values of Functions. So extreme values of functions, they help us answer questions like, what is the most effective dose of medicine? Or what is the least expensive way to pipe oil from an offshore refinery down the coast? The words that you're looking for are most effective or least expensive or least effective. In other words, graphs have maximums and minimums. These are maximums and these are minimums. And those are the points at which something usually important happens, like the most effective dose of a medicine. You might be giving somebody medicine and it's working and working. So you're like, I'll give them more. But at some point, it's too much. And then there's too many side effects and it's no longer considered effective. Our goal today is going to be to find those maxes and minimums. So there are two different kinds. There are local maximum and local minimum. But then there's also absolute maximum. So this one up here is not only a local max, local meaning it's just higher than any point around it, but it's also the absolute max, which means it's higher than everything. So one way to think about that is, let's say you've got the kid in our school that is the smartest. Everybody knows it. That kid is the smartest. Maybe they're the valedictorian of the class. So they, compared to everybody else around them, would be at the top. But you put that kid in all of Hunterdon County or all of New Jersey, and all of a sudden he might be local within his own school, but maybe he or she is not local overall. And then you take that kid that is local max for all of New Jersey, and you put them in the whole country, and maybe now there's an even higher maximum or minimum. So local is just higher than everything that's around you. Now in this particular graph, assuming that there's arrows on the end here that keep going, there is no absolute minimum. But that's not always true. If a graph were going up, then there would be an absolute minimum. So that's the difference between absolute max and min and local max and min. Let's do an actual problem. So I've been given f of x is equal to 1/3 x cubed minus x squared. I'm going to make a quick graph of it by taking out the x squared, and that gives me 1/3 x minus 1. If I set that equal to 0, I can find the intercepts. So I know that there's going to be a bounce at 0. I know that it's going to end up, and that this is its general shape. The other one, so sometimes you have to actually do it out if you can't do it in your head. That's always okay. Clear the fractions. X minus 3 is equal to 0. X is equal to 3. So I know it goes up, it bounces, it comes down like that. So it was very easy to find one of the local maximums. But what if I want to find that local minimum? Where was it at the bottom? So before we do that, let's talk about what happens when there's different domains. So we're going to look at it first on the domain from negative infinity to infinity. So right away, that means that there's going to be no absolute maximum because it goes up forever, and no absolute minimum. The local max is going to be 0. Notice that it is not 0, 0. Okay, this is the most important thing I'm probably going to say all day. The max or the min is the y value. Okay, the max or the minimum is the y value, not the x value, because I want to know how high it goes. It goes up to 0. So to find this point, does anybody know what we're going to do? We're going to take the derivative and we're going to set it equal to 0. So the derivative, y prime, is, now you know why there's a 1/3 there, so we could do 3. And we could get x squared minus 2x. I set it equal to 0. So this is the formula for the derivative. It tells me the derivative anywhere along the curve. But I specifically want to know where the derivative is equal to 0. So I factor, and I get x is equal to 0, which I already knew, and x is equal to 2. But don't put 2 here. The minimum is always the y value. So I'm going to relabel this f of 2, not just plug it in. Make sure you tell everybody what you're doing. 1/3 2 cubed minus 2 squared is 8/3 minus, now this is 4, but 4 we're going to have to convert into thirds, so 12/3, and that gives me negative 4/3. So was my graph accurate? No, it should have only gone like that, which is okay. It's just a sketch, but it still gave me an idea of what it was going to look like. But now I can graph it exactly. So my local minimum is going to be negative 4/3. But now let's change things up. Let's only go on the interval from -3 to 6. So I'm going to stop at -3, whatever that is, no more arrow, and then I'm going to go to 6. Now I can't see those 2 points, but what they did was they provided an absolute max and an absolute min. How am I going to find that? I need to know what that point is. 6 comma what? Because remember, this would be the absolute max. If you wanted to say 6, it would be, that's where it occurs. It occurs at 6, but what is the actual max? So we do 1/3, 6 cubed minus 6 squared, and we get, let's see, 36. And then for this point, -3 comma what? I'm going to put in f of -3, 1/3 -3 cubed minus -3 squared. And what does that come out to be? -18. So that is going to be my absolute minimum. Now there's still a local max there. So 0 is still one of the answers, and 36. So this is a local max and an absolute max. Because for everything around it, locally, it is the maximum, but it also happens to be the absolute maximum. So how does that affect local minimum? Same thing. -4/3 is a local minimum, but -18 is also a local minimum. All right, now I changed something up slightly different on the next one. I'm going to have the graph go from 0 now, but open circle. So from 0, open circle, and it's still going to go all the way up to 6. Okay, actually I'm going to take the arrows off. And it's going to go all the way up to 6, closed circle. So now my absolute max is still 36. And now I have an absolute minimum at -4/3. See how that changed? And it never, of course, reaches the -18. So that becomes both a local minimum, and now it's also the absolute minimum. Now 0 is no longer a max because it is a parenthesis. So it's an open circle. So my local max is just going to be the 36. I can't count the 0. All right, you can try this next one on your own if you want to. We're going to go from -3 to 1. We're going to go from -3, which luckily I already know -3 is 18. It bounces at 0. Oh, it doesn't matter. I'm just going up to 1. So let me figure out that point. F of -1, 1/3, -1 cubed minus -1 squared, -1/3 minus 1. Negative 4/3. That's a little ironic. That's what it was with the other one too. So -1, negative 4/3. So we know that this graph comes up and it does go like this, but they don't want us to draw it anymore. So, so now what do I have? If I stop this graph at -1, even though there's no bumps anymore on my graph, it's just a straight going up, that's still considered a local max and an absolute max. And then the -18 would be both my local minimum and my absolute minimum. So this last example leads us to the extreme value theorem, which is not complicated. They just gave it a fancy name, which says that if you have a function that's continuous, which this clearly is, then there has to be both a maximum and a minimum if it is a closed interval. Remember, on the open interval, it can mean you don't have a max or a min, but as long as it's a closed interval, it doesn't even have to have any curvature at all. It's going to have a max and a min. It might have lots of things, but if it's closed, it definitely has a max and it definitely has a min. Even if it's straight across, then the max and the min are the same point. And this is called the extreme value theorem. So of course, how do we find the extreme values? We just did it a minute ago. Derivatives. So this whole entire unit is applying derivatives. So you'll still be doing derivatives, but just as a tool for all the other problems that we're going to be doing. So this first section is a ton of theory. It gets a little bit annoying to some people, but necessary, sorry. If a function f of x has a local maximum value or a local minimum value at an interior point of its domain, and if f prime of x exists at c, then f prime of c is equal to 0. So here's the thing, you guys. You're going to have to know how to read calculus next year. You might have a terrible professor that you're going to have to read the book. So if you read this, just work it out. If a function has a local maximum or a local minimum at an interior point of its domain, so whatever the domain is, I'm going from here to here, let's say, and if the derivative exists, so it's continuous because, you know, here, this one is continuous, but there's no derivative there. No derivative. But if the derivative does exist, because it's nice and smooth, not pointy, then that derivative is going to be equal to 0. That's all that's saying. But sometimes a maximum or a minimum may occur when the derivative is not equal to 0. So we know that this is a minimum. So that's what this one's saying now. Even though there's no derivative, there still is a max or a min. So how could that happen? Cusps, corners, things like that, okay? They could have maxes and mins, even though the derivative is not equal to 0. So I don't want you to always put together derivative is equal to 0 is max or min. That's true, but in addition to that, the derivative might not be equal to 0, and you could still have, actually, not equal to 0, specifically does not exist. So anyway, somebody put together these two situations and called them critical points. It just is where the derivative is equal to 0 or where the derivative does not exist. In summary, extreme values can only occur at critical points. Critical points being where the derivative is equal to 0 or where the derivative does not exist, or it could occur at an endpoint. Most of our graphs don't end, but if you do have a graph that ends, then you could have a max or a min there. That'll come up much more often in word problems where the domain is something specific, like all the oil has spilled out, or the maximum number of people are on the ride, something like that, where there's a very definitive end. So another kind of exception. We're going to put this all together, but right now, like I said, a lot of theory in the beginning. it's important to note that a critical point does not necessarily indicate an extreme value. So think about this. We know what x cubed looks like. -1, 1, 1, we know that it goes up and kind of goes like that. So we know that it doesn't have any max or min right there. It just starts at the bottom and it goes all the way to the top. But if you took the derivative of it, you would get 3x squared. And you would say, oh, at x is equal to 0, the derivative is equal to 0. Well, that's true, but it doesn't mean it has a max or a min. So it is possible that a critical point does not necessarily indicate an extreme value. What is the bottom line of this whole thing? You're going to have to make the graph. You're really going to have to know what things look like. So let's make these graphs. I tried to pick two that you're not already familiar with to show you that you're capable now of making graphs, even if it's not something you're completely familiar with. X to the 2/3. So let's, first of all, I only need to go from -2 to 3. So -2, -1, 0, 1. I could do 2. I definitely have to do 3 and see where it stops. So -2 to the 2/3. That's not going to be a good number. -2 to the 2/3. -2 squared is 4, so cube root of 4. You might be thinking, I have no idea what the cube root of 4 is. Well, you know that the cube root of 1 is 1, and you know that the cube root of 8 is 2. So it's 1 point something. So at -2, it's 1 point something. -1, much easier. -1 squared is 1. Cube root of that is 1. 0. 0 to the any power is still 0. 1. 1 squared is 1. Cube root of that is 1. 2 is not going to be any better. 3 is not going to be any better. But 3 to the 2/3 is going to be 9. So cube root of 9, which, since we know the cube root of 8 is 2, should be a little bigger than 2. So at 3, it's actually going to be a little bigger than 2. So I think we can do one more. No, I was trying to decide if we should do one more to just give you shape. But this shape comes down like this. And I guess actually -3 would have been just as high. So it's a little more symmetric than I drew it. Okay, is that point perfect? No, but it is symmetric. How do I know it's symmetric? Because 1 and 1 produced, -1 produced 1 and 1 produced 1. That made it an even function, so I know it's going to be symmetric. So it says find the absolute maximum and minimum value. I didn't need derivative. I can just see it. So the minimum is 0. Now remember, this graph was supposed to start here, go down, and then go up to there. So the maximum value is going to be that 3 point, which is the cube root of 9. So let's say you didn't make the graph of this. Let's say you just went straight up for a derivative. Then f of x is equal to x to the 2/3. F prime of x is equal to 2/3 x to the -1/3. And you set it equal to 0. Then you would have gotten 2 over x, 3x to the 1/3. Is this ever equal to 0? It's never equal to 0. So that tells you something about the graph, that it doesn't have any smooth continuous points where the derivative is equal to 0. But also, you can see that it does have a domain. There's a point where the derivative doesn't exist. The derivative does not exist at 0. So if you had never made this graph, you still would have said something happens at 0. So the 3 points you would have checked were the critical point, which is 0. Remember, a critical point means where the derivative is equal to 0 or where the derivative does not exist. and you would have checked the endpoints. And that would have been where your max and mins came from. So you could have gotten the same answer without making the graph if you always do these steps: endpoints and critical points. Okay, so let's see if we can make that work for the next one. I'm going to do it backwards this time. This time I'll just try and do it algebraically and then do it graphically. And then after these two examples, you'll know which one you like better. So before I do the derivative, I'm going to change it to 4 minus x squared to the negative 1/2. The derivative is negative 1/2 4 minus x squared to the negative 3/2 times the derivative of the inside, which is negative 2x. The negative 1/2 and the negative 2 cancel, and I get x over 4 minus x squared to the 3/2. If you're saying to yourself, yeah, I have no idea what that graph looks like, then you just need to know where the derivative is equal to 0. Well, if I set this equal to 0, then it must be because x is equal to 0. So there could be a max or a min there. Where the derivative doesn't exist. So where doesn't it exist? What numbers can't x be? What would cause that denominator to be 0? Plus or minus 2. These two sets of answers, the 0 and the plus or minus 2, these are called critical points. But you also have to check the endpoints. So no domain is given, so you don't have to worry about endpoints unless the graph just ends. Sometimes a graph ends, right, like a square root graph, and it does have an endpoint just because of its domain. Well, you don't really know what this one looks like, so that's not going to be a good option in this case. You don't know what the endpoints are. So let's plug in these values, x and y, 0, negative 2, positive 2. So when I plug 0 into the original, remember we're doing y is equal to f of x. When I plug 0 into the original, I get 1/2. Oh, when I plug 2 into the original, it does not exist. Even in the original, I know that the derivative doesn't exist there, but even as a point, it doesn't exist there. So now how are you going to tell if it's a max or a min? Well, back to my, see, this is why I love to graph. Because if I could see the graph, then I would know. But another thing you could do is you could just test a point that was nearby. So, because I know something happens. This is either a max or a min. So just try another point. At 1, right, so at 0, it's 1/2. And at 2, it suddenly doesn't exist. But at 1, I get 1 over the square root of 3. And by the way, this is also an even function at negative 1. See how the answer won't change because it's squared? It's also going to be 1 over the square root of 3. I don't know what that is off the top of my head, so I'm going to quick plug it into my calculator. 1 divided by the square root of 3 is 0.577. So in other words, it's higher on both sides. So it turns out that this graph goes like this. It's kind of an inverted semicircle. And then once it gets to 2, it stops. It can't go any further. So in the end, to try and figure it out, I know that this is not just a local min, but this is also an absolute min. So you're going to be putting together where the derivative is equal to 0, where the derivative does not exist, and endpoints if you can figure them out. But you are going to want to make the graph. It just is easier. Okay, see if you can make this graph on your own. You should pause it and see if you can do it. But as you know, I'm going to do it for you. So I personally would rewrite them twice, and I would change this. So this is just an upward parabola, a downward parabola that's been moved up 5. 1, 2, 3, 4, 5. And then it goes down 2, and down 2, and that's the point that I actually want, so I'm going to, oh, it's closed. And it goes up to 5, and then, so down over 1, down 2, but normally I'd go over 2, down 4. I double it because of this -2, so it'd actually go down 8. So like that. And then this one is y is equal to x plus 2, but I need to start, normally I would start at the y-intercept, but I can't start until 1. Don't start at 2. It says x is greater than 1, but you still need to plot the open circle at 1. So you still need to plot 1. So at 1, it's 3. Now I have an open circle at the same exact spot that I have a closed circle, but it's like rock, paper, scissors. Closed covers open, so closed wins. And then it has a slope of 1. So it looks like that. So I'm not even going to do any derivatives. Totally unnecessary. I can see that the local max is up there at 5. And I can see the local minimum is right there. So local max is 5, and the local minimum is 3. And there is neither an absolute minimum or an absolute maximum because the graph keeps going. All right, so we're going to just do one of these on our graphing calculator so that you can see how that's done. And the last one of this type. So you probably don't know how to graph this absolute value. So I'm going to show you something really fun and tricky. And that is pretend the absolute value is not there. Y is equal to x cubed minus 9x. You know what that looks like. So you take out the x, you get x squared minus 9. Y is equal to x times x plus 3, x minus 3. And there's a 0, 0. If x is -3, there's a 0. And if x is +3, there's a 0. And this is an upward cubic function. So it looks like that. That is this graph. Now, to draw this graph, it's absolute value. That means every time that y is negative, it's actually going to become positive. So all these negative numbers down here are positive. These are already positive. This one is negative, so it's going to become positive. And this is already positive. How cool is that? That's how you graph it. When you know an entire function is absolute value, you can just graph the interior function and then take the absolute value of it by making it all positive. So where are their local maximums? So the local maximums would be these points. I don't know what those are. So I take the derivative and I set it equal to 0. I can see that it has a derivative equal to 0. So f prime of x, I don't need the absolute value to get that. I can just do it with f prime of x, and it should tell me that value. 3x squared minus 9, I set it equal to 0. And I get 9 is equal to 3x squared. 3 is equal to x squared plus or minus the square root of 3 is equal to x, which is approximately 1.7, which looks just about perfect. So there's local maximums of, actually I'm going to leave it as a square root of 3. Oh, that's the x value. How high is it? So remember that the maximum is always the y value. So square root of 3 to the third minus 9 square roots of 3. This looks a little hard to do, but it's really not, because the square root of 3 times the square root of 3 times the square root of 3. These two becomes 3 square roots of 3, and then minus 9 square roots of 3 is -6 square roots of 3. But remember, we're doing absolute value. And hopefully that answer just sounded wrong. You see what I mean? It was finding this point down here, which of course isn't correct. So the local maximum is at 6 square roots of 3. You don't need to state it twice, even though that's how high it reaches twice. There is no absolute maximum on this problem. Are there local minimums? Sure are. Okay, so local max is this. Local min, this one's a little easier. I can see that it goes down to 0 in 3 different spots, but you only have to list it once. Just a little refresher from differentiation. Does the derivative at 0 exist? No. Okay, that creates, when that curve went down and then came up and then went up like that, that is some kind of a cusp. It's coming down at a really steep negative slope, and then all of a sudden it's going up at a positive slope. That's considered a cusp. F of 3 also does not exist. Not a smooth continuous curve. It's not differentiable there. The derivative at negative 3 does not exist. But were we still able to determine extrema? Yes, because extrema can happen in 2 different places: when the derivative is equal to 0 or when the derivative does not exist. So you'll see that there's a little book section that you could look at if you need more help with this. All right, back to our graph. So this is what I drew in the beginning. There's your local max. This is your local minimum. Notice what's happening to the slopes. The slopes all the way along this curve for that whole section are positive. But once you reach the maximum, the slopes are negative. And then once you reach the minimum, the slopes become positive again. This is called the first derivative test for local extrema. If the derivative changes, so derivative is slope. So if the slope changes from positive to negative at a critical point, then there's a local maximum. If the derivative changes from negative to positive, then there's a local minimum. If it does not change sign, so something like this, positive, positive, okay, it does get narrower, but then it's still positive, then there is no critical point. That is called the first derivative test for local extrema. How do we use that? Again, for people that don't want to graph, you could sit there and say, well, I'm just going to find the derivative, 2x minus 12. I'm going to find the critical points. 12 is equal to 2x, x is equal to 6. And then you're going to make, and you're definitely going to want to do this, you're going to make a y prime chart with whatever the zeros are on it. So at x is equal to 6, I know that the derivative is 0. If it's not 0, it has to either be positive or negative. So I can find out if 6 is a max or a min by finding out if before 6 the slopes were positive and then they became negative, or 6 is a local minimum if the slopes were negative and then became positive. So you're just going to test a point in the derivative. I want to know about the slopes before 6. So if I put in a number like 3, 2 times 3 is 6 minus 12, it's negative. And I'm putting a bunch of them because even though I only tested one point, I could have tested any point and they all would have come out negative in that interval. If I tested a number bigger than 6, like 12, then 12 times 2 minus 12 is definitely positive. And I picked 12. I could have picked anything and it would have come out that way. So I know this graph, whatever it looks like, you know what it looks like. Whatever it looks like has a negative slope and then a positive slope. Oh, it's parabola. So if you're thinking, I'm just going to graph it, Mrs. Shaffer. First of all, that would make me so glad. But what about when you get this? You're not going to be able to graph everything. So this is where this derivative test is really going to save you. So let's do the derivative. I know you're very excited about this. The second times the derivative of the first plus the first times the derivative of the second. Remember, the derivative of e to the x is just e to the x. I set it equal to 0 to find the critical points, and I get 2x plus x squared minus 3 when I take out the e to the x. I'm going to rearrange that so that it's a little more factor friendly. And then I get e to the x times x plus 3 times x minus 1. So either e to the x is equal to 0, or x plus 3 is equal to 0, or x minus 1 is equal to 0. So my critical points are at -3 and 1, and when is e to the x equal to 0? Okay, never. If you're in honors, you need to put that in your appendix. And this graph, if you're in AP, you need to memorize this. This is the graph of e to the x. There is an asymptote at 0. So right there, it has an asymptote. It's never actually going to be 0. And just for the record, the graph of e to the negative x, you will need to know that one too. Looks like this. And where do they cross? They cross at 0, 1. So a couple things you need to have memorized is the e to the x graph, or honors. Put those two charts in your appendix. So luckily, this is never equal to 0. It's always positive. So when I put things on my sign chart, I don't need to worry about it. -3 and 1. This labeled y prime, because eventually we're going to have a y double prime sign chart. So -3 is where y prime is equal to 0, and x is equal to -1 is where y prime is equal to 0. So that means that they're like peaks. And before that peak, before it gets to that peak, the slope is either negative or the slope is positive. So we're just going to test a point. We want to know what the slope is, so I'm going to put it into the slope equation. So here's an easy way to do it. Just put it into the factored form way at the end. So right here, this is still g prime of x. If I put in, say, a 5, 5 would make this positive, and this is always positive. So it's definitely going to come out to be positive. So this graph, whatever it's doing, is rising. And then between -3 and 1, I can test 0. 0 would make, this is always positive, but this would make this negative. Now, some of you already think to yourself, this is definitely going to be positive. It is. You can test a point, and you can confirm that that's positive. But please, please, please do not get sold on the fact that it's always going to go positive, negative, positive. It definitely is not. There's going to be times where a graph has a dip, and then the next one, it just keeps going up. So it's positive. The slope may be 0 just for a second, just while it's like kind of leveling out, and then it's positive again. So it will not always go positive, negative, positive. So be warned. So what are the extreme values? There's one at -3 and there's one at 1. We actually didn't find it though, did we? This is going to be a max. This graph goes up and then down and then up. So there is a maximum at x is equal to -3. How do I find that max? G of -3 is 9 minus 3 is 6, e to the -3. So 6 over e cubed. That's the maximum this graph ever obtains. It's a very small number, 0.299. G of 1 is 1 squared minus 3 is -2 e to the first, which is approximately negative 5.43. So you might be thinking, how can that be a min and that be a max? This number is higher. Remember, the max and the min have to do with everything around it. So apparently at negative 3, it's only up here at like 0.2 something. And then at 1, it's way down here at negative 5. 1, 2, 3, 4, 5. So max and then min. Okay, that's approximately what it looks like. Is it polynomial? No, it's got an e in it. So probably something else happens. Maybe it goes up and then it goes like that. And then it goes up and it levels out. We don't care about that part of the graph. All we care about is that there's some kind of a max there and some kind of a min there. That is the max. Actually, yeah, I was going to say it's local max. To say it can't go all the way up, but it could for an absolute. So there's a maximum there and a minimum there. Okay, one more time. Back to our graph. This is actually very cool. So at times, the graph is going to be concave up. So all this section is considered up. It makes a U for up. And some people like to think it holds water. And other times, the graph is concave down. So I know there's convex and concave, but in math, we just have concave up and concave down. Concave up and concave down. There's no convex at all. Concavity can be determined using the second derivative. If you are really into this, you could stop and see if you could figure out why that tells us that. Why does the second derivative tell us whether or not it's going to have that curvature? So if I told you that the first derivative is positive, then the first derivative could be positive like that, or it could be positive like that. All that, that's all positive slope. Or it could even be positive like this, right? All of these are positive slopes, and yet very, very different. This one has zero change. The slope stays the same, no change. So think about that in terms of derivative. Y is equal to something like, let's say, 2x plus 1, right? Because it's a line. And then y prime tells you its slope along the way. Y double prime is the change in the slope. But since there's no change in the slope, the second derivative tells you that it's constant. And that's how I know if it's concave up or concave down. Where this one has some kind of a change in it. So first, it's really steep, but then it's less steep and even less steep. So what's happening to the derivative? The derivative, which is the slope is decreasing. The slope is not negative, but it's becoming less positive. So its second derivative is going to be negative. It's a negative second derivative because it's becoming less and less positive. This one is a little positive, more positive, more positive. It's getting really steep. What is its change? Its change is positive. It's becoming more and more steep. So when you have a positive second derivative, that means it's going up. That's the theory behind it. But honestly, you can just memorize this. This is all you need to know. If that was like, I kind of get that, then it's concave up where the second derivative is greater than 0. It's concave down where the second derivative is less than 0. And that point right where it happens, where you no longer considered it down, you kind of start considering it up, that's called the point of inflection. And a point of inflection might occur when the second derivative is 0, because right there, there's no change. Or when the second derivative does not exist. Does that sound familiar? Okay, those are going to be the critical points for this. Where the second derivative is equal to 0, where the second derivative does not exist. And we have a couple examples, I think 3, to show you on that. All right, use the concavity test to determine the concavity of each function. So even if you didn't graph it, y prime is equal to 2x. So using our first derivative test, always label, it's equal to 0 at 0. If you put in a number bigger than 0, it's positive. And if you put in a number less than 0, it's negative. So now I know this graph is falling and then rising. So I already can see that it's concave up. But second derivative is 2, which is positive, always. So that would indicate that it's always concave up, which of course it is. 0, 0, 1, 1, 2, 4. 0, 0, 1, 1, 2, 4. Always concave up. So the algebra and the matches, the calculus matches the graph. Same thing here. Y prime is equal to, the 3 will cancel, cosine of x, and y double prime will equal to negative sine of x. Where is cosine equal to 0? So I'm going to make my y prime chart. And cosine is equal to 0 at pi halves and at 3 pi halves. So what is it doing in between? Well, before pi halves, so try and picture your cosine graph. Before pi halves, cosine is positive. And then, so I'm not plugging something in, I'm just looking at the graph. And then between pi halves and 3 pi halves, cosine is negative. And then from 3 pi halves on, well, just until 5 pi halves, but we don't really need to go that far. 3 pi halves on, it's going to be positive again. So what does that mean for my graph? This tells me about the slope. So I know it's going to have a positive slope until pi halves, positive slope until pi halves, and then it has a negative slope all the way until here. So 3 pi halves must be a minimum. I know you already know what it looks like, but I wanted you to see, look at this, see, negative slope all the way down there. But what does sine do? When I tried to draw it without knowing, like I know it goes up, but does it go up like this or does it go up like this? Well, of course, you know how it goes up, but watch how the second derivative can help me with that. Second derivative is equal to 0. So when is sine equal to 0? At 0, at pi, at 2 pi. So at first, sine is positive, but since there's a negative there, it's going to be negative. And then sine between pi and 2 pi is negative, but since there's a negative there, it's going to be positive. So this means that it's since this is my y double prime chart, concave down, concave up. Slope is positive. Slope is negative. Slope is positive. So look at that. Look how perfectly that matches. The slope is positive, then at pi halves, the slope is negative all the way to 3 pi halves, and then the slope is positive again. But in terms of concavity, see how it's concave down through this whole section. And then right there, you might think it's still concave down, but now they consider it concave up. That's what gives that beautiful curvature that we see in trig functions. It changes concavity right at that moment. So there. It's concave up, and now it's concave, or it's concave down, and then it's concave up. So hopefully you see how first derivative, second derivative will really let you make a graph quite accurately. Last one. Y is equal to e to the negative x squared. First graph of the day that we don't know what it looks like. So this is where we're really going to put our skills to the test. First, y prime. So the derivative of e to the u is, so I'm just going to write it up here, negative x squared is e to the u times du. The derivative of this is negative 2x. And then the second derivative is going to be product rule, the second times the derivative of the first, which we already know is e to the negative x squared times negative 2x, plus the first times the derivative of the second. I can take out a negative 2, and I can take out the e to the negative x squared. Now be careful here. You're left with this negative 2 in both x's, and even though you took both of these out, you are left with 1. So don't think that there's nothing left there. You are left with 1. Okay, so let's make our two sign charts. So on the first one, where is this equal to 0? Only when x is 0. There's 3 factors. Remember, e to the anything is never equal to 0. So it's just this factor that could be equal to 0. So now, even though it's e to the negative x squared, it's still going to always be positive. So when x is positive times a negative, it gives me a negative. When x is negative times the negative 2, it's going to be a positive. So I know that this graph is rising and then falling, but maybe it's rising and then falling. Maybe it's rising and then falling. This would be concave down the whole time. This would be concave up and then concave up again. And this would be no concavity. So knowing how to graph this is really critical. But I do know I can plot one point. There is some kind of a max, no matter which one I draw, at x is equal to 0. So 0, comma, anything to the 0 power is 1. That is going to be the max of my graph. All right, so let's figure out the concavity. 0 is equal to negative 2 e to the negative x squared. I don't know why we wrote, oh, just because of the 0. Negative 2x squared plus 1. So this is never equal to 0, right? This is never equal to 0. So we're really just looking at this one. 1 is equal to 2x squared. 1/2 is equal to x squared. This is ugly. Square root of 1/2 is equal to x. You're like, oh no, I got to put this on my y double prime chart. Negative the square root of 1/2 and positive the square root of 1/2. Don't worry. You can test whatever points you want. Even though this is the square root of 1/2, you can test 5. So if I plug a 5 into this equation, then 5 squared is 25 times negative 2 is negative 50 plus 1 is, and the bottom line is this is definitely going to come out to be negative. This is negative, and this is always positive. So you get a positive number. See how I didn't actually have to plug in that square root of 1/2? And come on, what's a nice easy number between negative square root of 1/2 and positive square root of 1/2? 0. So if I plug in 0, I get a positive. This is always positive, and this is negative. So I get a negative. And then before this, I'm just going to plug in negative 10. So negative 10 squared is 100, but times negative 2 is negative 200 plus 1. The bottom line is this is going to be negative, and that's negative. So this is going to come out to be positive. I know it reversed again, plus, minus, plus. It's not always going to do that, I promise. So how do I draw this graph? Something happens. This is a point of inflection. How are you going to change the inflection? It's got to be somehow concave down, but then somehow concave up. How does that happen? Because the slope never became positive again. The slope has to stay negative, but somehow change its concavity. So we're going to bring back one more thing. Don't shoot me. we are going to bring back limits. This is the last thing you need to make a really great graph of a function you've never heard of. What is the limit as e to the negative x squared approaches infinity? Think about it. It's an e-graph. E-graphs always have asymptotes. And sure enough, you can't just plug it in. But if I simplify it to 1 over e to the x squared, if you plug in infinity, you're pretty much going to have 1 over infinity, which is 0. So this has an asymptote. Remember, it's an even function. I don't need to do the limit as I go to negative infinity because it is also going to be 0. So it has an asymptote, and then somewhere in some really tiny number, it's going to change its concavity. So the slope is always positive, but you see that little like curvature change? It's going to have a little curvature change. I didn't draw that one as nicely. Still didn't, close enough. Okay, so there's a little curvature change that happens right at that point of inflection. Find the, what was the question again? Don't even remember. That's how you put all these things together. Limits, first derivative, finding first derivative found max and min. Second derivative found concavity and points of inflection. Limits helped you get asymptotes. And all together, they allowed you to make a graph that otherwise you probably wouldn't have been able to graph. So the maximum is 1 for this graph. That's the only local extrema. Okay, so just in case you're wondering, is this video ever going to end? These are the last 3 problems, and then we'll end part 1. So the second derivative test for local extrema is not something that I actually use very often, but I'll teach you how to do it, and if you like it, you can use it. So when I have this, I can tell if something's a max or a min just if the derivative changes from positive to negative. But somebody came up with this other test, so we'll use it. So let's find the first derivative. First derivative is equal to 3x squared minus 12. Second derivative is 6x. So what this test says is if the first derivative is equal to 0. So where is this equal to 0? 3 times x squared minus 4, 3 times x plus 2, x minus 2. So my critical points, the numbers I would normally put on my sign chart, would be plus or minus 2. So if it were me, I would make a sign chart. I'd put in the minus 2, I'd put in the plus 2, and I'd figure out if this was a max or a min based on whether or not this was plus minus or minus plus. So what they're suggesting, instead of making the sign chart, it says, and the second derivative is less than 0. So I take the second derivative, I plug in 2, and I get 12. That's positive. It says that if your critical point, where the derivative is equal to 0, if the second derivative is positive, then that's a minimum. So there is a minimum at x is equal to 2, okay? And the minimum is, so 2 cubed is 8 minus 24 minus 5 is, what is that, negative 21? That's the minimum. Okay, so this number 12 doesn't tell you what the minimum is. Oh, I wrote x is equal to 12. X is equal to 2. But it tells you just that it's positive. Let's try the other one. F of negative 2. So when I plug a negative 2 in there, I get negative 12. Again, the 12 doesn't really matter, just that it came out to be negative. So this second derivative test says if the second derivative comes out to be negative, then it's a maximum. So now I know that there's a maximum at x is equal to negative 2. And then I could plug negative 2 in to actually find the maximum. So the maximum is, what do we get when we plug that in? Negative 2 cubed is negative 8 plus 24 this time, minus 5. So negative 13 is 11. Okay? Now, hopefully you're asking, why does that work? Here's why. Because if you have something that is either a max or a min, it's either going to be concave up or concave down. So what they're saying is, okay, I know something happens at 2, and since its concavity is positive, it must be going up. And if the concavity is positive and it's going up, then it must be a minimum. It is a pretty cool idea. And for this one, they're saying at -2, I know that there's a concavity down, so it must be a maximum because it has a negative concavity. I still prefer to make a sign chart. All right, last two. Y prime is equal to 4x to the third, and that is equal to 0 at x is equal to 0. Y double prime is 12x squared, so I plug this in, f double prime as 0, and I get 0. Well, now what am I supposed to do? That's not on my little chart here. So on my chart, it tells me what to do if the second derivative is less than 0 or greater than 0. The test fails if it's equal to 0. Fail. So you're going to have to go back and do it my way. So at 0, you make your y prime chart. And remember, when you plug things in, plug test points into y prime because we're trying to find out the slope. So the slope of a number like 1 is positive. The slope of a number like -1 is negative. So this graph falls and then rises, so there is a minimum at x is equal to 0. And the minimum is f of 0, which also happens to be 0. But remember, you always have to plug it in, the y value. The y value is always the minimum. Last one. So I'm going to just change this to x to the 1/3. F prime of x is equal to 1/3 x to the -2/3. F double prime of x is equal to -2/9 x to the -5/3. So you have to find the critical points in order to use this method. So 1/3 x to the 2/3. But where is the derivative equal to 0? The derivative is never equal to 0. And this test requires the derivative to be equal to 0 to use it. So again, the test fails. So was I selective in my examples? Of course I was. Because in general, this just isn't that useful. But unfortunately, AP kids, I have seen it on the AP test where it specifically says use the second derivative test. So you do have to know it. And like I said, it does make a lot of sense. If it's, if a point is concave up, it has to be a minimum. And if a point is concave down, it has to be a maximum. But there's the sign chart always works where the second derivative test does not. All right, there are 2 more videos for this, but this is the only one that you have to do for today. Have a great day.